Next up, we want to take a look at the Kirchhoff circuit rules. Now you'll recall that there are two different rules for analyzing multi-branch circuits. The first rule is called the loop rule. And the loop rule tells us that around any closed loop, the sum of the voltages is equal to 0. And we'll remind ourselves that this is a consequence of conservation of energy. If you went around a loop in a circuit and every time you went around that loop you gained voltage or you gained energy per charge, that would violate conservation of energy. And so you end up with what you start. The sum of the voltages around any closed loop in a circuit is going to be 0. And this is a consequence of the fundamental principle of conservation of energy. Conservation of energy. So if you want to write that down, you can, but let's go on. Okay, so after you have the loop rule, the second of the Kirchhoff circuit rules is the junction rule. And that says that the sum of the currents going into any junction must be the sum of the currents leaving any junction. So the sum of the currents going in must equal the sum of the currents going out. And so, of course, if I have a current coming in like this, and the current forks into two branches, say that's I1, and that goes to be I2 and I3, then we can say the current going into this junction would be I1. That has to be the sum of the currents coming out, so we could say that I1 equals I2 plus I3. And that is the junction rule. And that one's actually pretty easy to apply. The loop rule, however, has a little bit of a trick to it. When you have a circuit that has multiple batteries in it, it's possible that a stronger battery might overpower a weaker battery and force current through it in the wrong direction. And so current going through that weaker battery would not gain energy but actually lose energy because it's going in the wrong direction. And so we have to have sign conventions. When we add up the voltages around the loop, we have to know whether we're gaining energy or whether we're losing energy. And the way we do that is as follows. First, let's consider a convention for batteries. Now again, this is applying a loop rule. So we're considering a closed loop in the circuit, and we're imagining a charge traversing through that loop. And we're asking ourselves, what happens to that charge as it goes through each circuit element? Does it gain energy or does it lose energy? So as we follow our loops around the circuit, we apply these rules. So let's imagine we're looking at a battery that's in the circuit. And so our loop, we pick a direction of a loop. So let's say our loop is going this way. And as the loop goes through this battery, it's actually coming out the negative terminal. The negative terminal being the smaller one and the positive terminal being the larger one. Regardless, whenever the loop comes out of the negative terminal, and this is the loop, when the loop comes out of the negative terminal there, we say that the voltage is a negative voltage. That would essentially be the loop going the wrong way through the battery, so that as it goes through the battery, it loses voltage or it loses energy rather than gaining it. Now let's consider a battery oriented this way. Again, our loop is going to the right here. This is our loop. And our voltage is such that when the loop comes out of the battery, it exits the positive side of the battery. So that means that we get a positive voltage as the little charge in our loop goes through the battery. And again, keep in mind, these loops are all imaginary. They're just a mathematical construct to help us write down the right equation. So the currents that we imagine are real, but the loops are imaginary. The next thing we want to look at is resistors. So imagine a resistor and it's got a current going through it. We've already assigned which way we think the current is going, and we'll see how to do that more specifically when we look at some examples. But we've assigned a current going in a particular direction, and then we define a loop, and we look at which way the loop is going, and in this case we see that the loop and the current are going in the same direction. And so if this resistor is a resistor R, you would have a voltage of minus IR. Minus IR. And so it's minus when you have, that's just Ohm's law there, it's minus when they're in the same direction. So the same direction of the loop and the current means that you get minus IR. Now let's consider the opposite situation where the current's going in one direction, in this case to the right, and the loop is going in the opposite direction, in this case to the left. In that case, you would get a positive voltage. V would be equal to positive IR. And so these are our sign conventions when we're looking at the loops. So we're applying the loop rule. We're saying we've picked a loop in our circuit, and we're saying, okay, the sum of all the voltages around that loop is equal to 0. So we look at all the batteries and all the resistors in that loop, and we apply this rule. If the loop is coming out of the negative terminal of the battery over here, we have a minus V. If the loop is coming out of the positive terminal of the battery, we have a positive V. If the loop is going through a resistor, we compare it to the current. And if the current is in the same direction, we get a minus IR voltage drop. That's just from Ohm's law. But if the current is in one direction and the loop is in the opposite direction, we get a voltage gain of positive IR. And so that's what we do. We look at every resistor, every battery, we add in each of those voltages in our loop, and we set it equal to 0. So let's look at some examples and see how this can work in real life. Okay, here is the example that I stole from the internet. We have a 5-volt battery right here and a 7-volt battery right there. And then we have 3 resistors, a 560 ohm resistor labeled as R1, a 1.2 kilo ohm resistor labeled as R2, and a 1.2 kilo ohm resistor labeled as R3. And we can see there's a ground right here. That just means that the voltage of that terminal is 0 and the voltage of that terminal is 0. And so we've connected the batteries to a common ground. Here we have the positive side of the battery and the positive side on this battery, and then the negative terminals, which are, as I said, connected to the ground. So let's apply the Kirchhoff rules. What do we want? We want to be able to find the voltage across any resistor. We want to find the current through any resistor. We want to be able to find the power dissipated by any resistor. How do we do that? The secret is to use the Kirchhoff circuit rules and find all the currents. Once you have the currents, you can use Ohm's law, V equals IR, to find the voltages. And then once you have the voltages and the currents, you can calculate the power. So the first thing we want to do is pick a battery. I like to pick the leftmost battery. Some people like to pick the largest battery. It doesn't really matter. Pick a battery and start with that battery and assign currents to the circuit. So I'm going to start with this battery here, and I'm going to let the current go this way. And when I get to the junction here, there's the junction, the current's going to split. And so some of the current's going to go like that, and some of the current's going to go like that. And so I'm going to label this current here as I2. The current coming out of the battery, I'm going to label as I1. And the current going through this R3, I'm going to label as I3. Now this I3 continues through this loop. It goes through that battery as well, so this is still I3 here. And then it continues. Now what happens at this junction? I2 and I3 combine, and they come back to be I1. Now technically we should say that that's I4 there, but clearly just by inspection we can see that that's going to be I1. So we can save ourselves a little bit of time by skipping that step of labeling that as I4. Once we have the currents labeled, we can apply the junction rule. We have two junctions here, but they give you the same result. What they tell you, the currents going in has to equal the currents coming out. So if I pick this junction, the current going in is going to be I1, and then you've got I2 going that way and I3 going that way. So we can write, based on the junction rule, I1 equals I2 plus I3. And so that is the junction rule applied there. The next thing that we can do is draw the loops. Now, I'm going to pick a loop going through the left side of the circuit, so that's going to be one completely closed loop. And then I'm going to do another loop on the right side of the circuit, and so that's going to be another completely closed loop. And so those two loops together cover every element in the circuit, and so that's all I need to solve for the currents. Now we're going to apply our rules for the loops. And so let me draw in my direction. I'm going to go clockwise because I feel like going clockwise today, and I'll do that for both of these loops. And I'm going to call that loop 1 and that loop 2. And now I can apply for loop 1 the loop rule. Now keep in mind, my loop is going clockwise, so that means it's going like this, over and over. And so when it comes out the battery and it leaves the positive terminal, the bigger one, it's leaving the bigger one, and so that means that I get a plus 5 volts. The current going through R1 is 560 ohms. And as I continue through that loop, I'll see that the next thing happens is that it goes through this R2, which is 1.2 kilo ohms. And again, the current and the loop are going in the same direction. They're both going down. And so I get a minus I2 R2, or in this case, minus 1200 ohms, that's 1.2 kilo ohms, that would be 1200 ohms, times I2. And then as I continue going around the circuit, I'm back to the battery and I've completed my loop. And so once I complete my loop, I know that I can set the whole thing equal to 0. And that is the sum of the voltages for loop 1. Now we can do the same thing for loop 2. As I go through loop 2, I can see I'm going to come out the 7-volt battery on the negative side of the battery, so I'm going to get a minus 7 volts. I continue through this loop. I'm going up here. The current I2 is going down. My loop is going up through this part of the circuit, and so that means the current in the loop are in opposite directions, and that means that the voltage through that resistor is going to be positive. As I continue my loop, I next go through this resistor, and the current and the loop are now again going in the same direction, and so that one's going to be negative, and then I'm back to the battery so I can set it all equal to 0. So let's write all that out. We've got a negative 7 volts, and from there we go up here and we get a positive 1200 ohm I2. And then as we continue our loop, we go here and we get a negative 1200 ohm I3. And again, that completes the whole loop. And I'm back to the battery, and so I can set it all equal to 0. And those are the 3 equations we have. Now don't forget, the thing that my students do sometimes that confuses them is they forget they have this whole other equation up here from the junction rule. So this is one equation. The loop equation gives me a second equation. This loop equation gives me a third equation. So I have 3 equations and 3 unknowns. At this point, the physics is all done, and it's just algebra. So how would we handle the algebra? I'm not going to work it out to completion, but I'm going to kind of give you some hints of how to approach these kinds of problems. And of course, any of you that have had linear algebra may have learned how to solve systems of equations like this using Cramer's rule. And if you know how to do that, that's really the fastest way to approach a lot of these problems. But if you don't know how to do it that way, just plain old brute force works great. And that's the way I teach it because not everyone's had linear algebra by the time they get to physics 2. And the process is very simple. The idea is you've got 3 equations and 3 unknowns. We want to convert this into a system of 2 equations and 2 unknowns, and then keep iterating downward so that we have ultimately 1 equation and 1 unknown. Then we can just do regular algebra and solve. So I look at this and I see this I1. What I would do is I would take this I1 here and I would plug it into there. So if I do that, I would have that equation would become 5 volts minus 560 times I2 plus I3 minus 1200 I2 equals to 0. And when you simplify that, you end up with 5 volts minus 1760, that would be the minus 560 I2 minus the 1200 I2 gives you minus 1760 I2. You distribute this to the I3, you're left with minus 560 I3 equals to 0. And so by plugging this I1 into here, this equation turns into that equation. And what you have now are these 2 equations that I've circled in green. Here we have an equation that has as an unknown I2 and I3. Here we have an equation that has as an unknown I2 and I3. And that's just 2 equations and 2 unknowns. So I could do the same thing. I could solve this guy for I3, plug it into there, and then I would have an equation that only had I2 as an unknown, and I could solve for I2. Then I could take my I2 and plug it into here and solve for I3. And then once I have both I2 and I3, I could plug them up here and solve for I1. And when I do that, I get the following answers. So I end up with I1 being 0.0014 amps, I2 being 0.0035 amps, and I3 being 0.0023 amps. But when you do the algebra, you end up with this one being negative. And if you remember, all that minus sign means, so you go through all this, you find the current, that gives you the magnitude of the current. And when you originally set up the problem, you had to guess which way you thought the currents were going. You said, I'm going to start with this battery, and every time I get to a junction, the current's going to fork. And so you just drew which way you thought the current should go. If you end up doing the math and you end up with a current being negative, that just means you guessed wrong in your initial picture. It doesn't mean you have to go change anything. You've got the answer now. What are the 3 currents? This is the current I1, this is the current I2, this is the current I3. So you can effectively ignore those minus signs once you get to the final answers, but just know that that's what it means. You guessed wrong when you picked which way you thought the current should go. And that's how you do these problems. Let's look at another. Okay, here's a circuit that we analyzed previously using combinations of series and parallel resistors. But we can also use the Kirchhoff circuit rules to analyze this circuit as well. Even though there's only one battery, the rules will still work. So let's see how that can work. First, let's assign some currents. So the first current I'm going to have coming out of the battery, I'm just going to call I. And then it gets to this junction right here, and it's going to split. And so I'm going to have a current coming down this way and a current going that way. And I'm going to call that I1, and I'm going to call that one I2. And so I've applied my current at the junction rule. The current splits at the junction, and I can immediately write down an equation using the junction rule. I can say that I is equal to I1 plus I2. And I2 is going to continue along here until it gets to this junction, and then right here, I2 is going to split, and I'm going to call it I3 going down this way, and I4 going that way. So I've drawn those in just again, so I've got my I1 comes here, it gets to this junction and it forks, and so my I splits into I1 going down and I2 going across. Then I2 gets to this junction and it forks into I3 and I4 goes all the way around here. And I can immediately apply my junction rule there, and I can say that I2 is equal to I3 plus I4. And that's going to be one of my circuits, or rather one of my equations for analyzing the circuit. Now, this I4 here, as it comes down, when it gets to this junction, I3 and I4 combine, so I'm going to have I2 along this branch here, and then I1 is coming down, I2 is going that way, they're going to recombine into I going back to the battery. I hope that's clear. My picture's a little bit messy. It's not so easy to write on my iPad this way, but hopefully that all makes sense. But that gives us two equations for our junction rules, and we have quite a few unknowns. We've got 1, 2, 3, 4. Oops, that's 1, 2, 3. That's still 3, 4, 5 unknowns. We have only 2 equations so far, so we need some more equations. But we can come up with some loops and apply our loop rules as well. Okay, the first loop that I want to do is a loop that comprises of the battery and the R1 resistor. So if I'm considering the loop, I'm going to go around the box like this, and I'm going to choose to go in a clockwise fashion. And so that's going to be my first loop. And I can draw that in with this. And so I'm going to be going in where the green is my loop, and I'm choosing to make my loops all go in the clockwise direction. And that's a very simple, straightforward loop. And I can apply my loop rule, because if I look at my loops, I'm going this way, and so when I come out the battery, I'm coming out the positive terminal, so that's going to give me a plus voltage, and I know the voltage is 10 volts, so that gives me a positive 10 volts. Positive 10 volts. And then as I continue around my loop, I can see that I'm going to have the current I1 going through the resistor R1. They're going in the same direction. The loop is going down. The current I1 is going down. So that means I get a minus I1 times R1. And we know that R1 is 100 ohms. So I can simply write in I1 times 100 ohms. And all that's going to be equal to 0, because once I get past that resistor, I continue the loop and I go straight back to the battery. And so that gives me that equation, and I can even be a little bit anal and put in the right units there, ohms for the resistor, and that's that equation. Now look, this equation is actually really easy to solve. We'll do it in a second, but I've got 10 volts, I've got I1 as my unknown, I've got 100 ohms here. It's very easy to solve for I1. We'll do that in a second. But let's pick another loop. Now for my next loop, I'm going to start again at the battery, and I'm going to go around this one. So I'm going to go from here all the way around here like that. And so that's going to be my loop 2. And we can say that my loop 2 is going to be in yellow, and I'm just going to go around like that. Again, I'm going to go clockwise in my path. And so if I write down my voltages from my loop rule, I get for loop 2, again, I'm going to get the positive 10 volts. And then I'm going to get, as my loop traverses the circuit, I'm going to get minus I3 times R2, which is 200 ohms. And so that's going to be minus I3 times 200 ohms is equal to 0. Because once I get past that resistor, I come back and there's nothing else. I go all the way to the battery, and that's that. And then for my third loop, I'm going to choose to go around the entire perimeter. So I'll start at the battery, I'll go around this way, and then I'll come back to the battery. And again, I'm going to have a positive 10 volts here. Let me draw the loop here. My red loop is going to be my third loop. And so I've got positive 10 volts coming out the battery. I come here, I go through R3, and the current that's going through R3 is I4, and R3 is 150 ohms. And then I'm going to go minus IR because they're in the same direction. And then the current and the loop both continue through R4 in the same direction. And so that'll give me a minus I4R4, and I can write that out. So that's going to be minus R3 is 150 ohms. There's 150 ohms. And that's I4. That's ohms. And then it continues, the loop continues through R4, so I'll also have a minus R4, which is 50 ohms. There's 50 ohms right there. And then I have gone through everything. I go back to the battery, and so I can set that equal to 0. And look at what I have here. I've got this equation only has one unknown, this equation only has one unknown, and this equation only has one unknown. Oops, and I'm missing an I4 here. So I can put that in, that's I4 there. And so these two guys, that one and that one, they combine and give you, I can rewrite this equation as 10 volts minus 200 ohms I4 equals to 0, and that equation is easily solved because it only has one unknown. This yellow loop equation is easily solved because it only has one unknown. This one is easily solved because it only has one unknown. And then once I have I1, I3, and I4, I can solve for I2, and then I can solve for I if I need it. And so there's a couple of things I want you to notice here. Before we go on and solve this, I2 didn't actually go through any resistors or any batteries. I2 did none of that, so it's perfectly fine for that to happen that way. We still use the equation in here to solve for what we want. But once we do our algebra, answers work out to be pretty straightforward. I get, when I do the algebra, that I1 is equal to 0.1 amps, and that's the one going through the 100 ohm resistor. And then we have that I3 is equal to 0.05 amps, and that's the one going through the 200 ohm resistor, which is this R2 here. So R1, what's going through R1 here is this 0.1 amps, and what's going through R2 is this 0.05 amps. And then I get that I4 is equal to 0.05 amps again. And that's the one going through R3 and R4. It's going through R3 and R4. And so if you look back at what we did previously, you'll see that that's exactly the same answers that we got doing parallel in series circuits. And if we want the total current, we know that I was equal to I1 plus I2, but I2 was equal to I3 plus I4, so we can say that I is equal to I1 plus I3, I3 plus I4, and when we plug that in, we get that the total current I is equal to 0.2 amps, and again, that's what we got when we did series and parallel circuits. So this technique gives you the same answer. It works just fine this way. I'll let you decide whether you think it's easier or harder to do it this way, but you do need to understand how to do it both ways. But anyway, hopefully this review will help you get ready for the next Mastering Physics, which is up, and we'll continue on with RC circuits in the next video.